So let us introduce the last speaker of today's session, Mariana Olvera-Cravioto from Chapel Hill. So she's going to talk about stochastic recursions on directed random graphs.
Thank you. Thank you for the invitation to speaking here today. The session has been quite interesting, and most people have been talking about, of course, interacting particle systems in some sort of graph. So I'll give a slightly different version of this, where the graphs that I like to work on usually are finite by nature, are large in the essence of the problems that we're trying to analyze. And in this particular case, they're going to be directed. So I'll give you a little bit of an overview of some well-known problems that fall into this category, and talk about at its core of techniques that allow us to say something interesting about the behaviors of a general class of stochastic processes on this kind of finite large graphs. So let me start by saying that we're gonna work on a family of directed graphs with a vertex set Vn. N is usually very large in most contexts, and a set of edges En, which is of order n. So unlike many of similar settings where people analyze interacting particle systems, this is a sparse graph, right? And sparsity is important to us because in many of the applications that I'm interested in, these are random graphs these are social
Mariana,
networks.
we're still seeing your first slide.
Oh,
Is that okay?
I'm showing that it's displaying. So if I do this, can you see the next one?
Yes.
Okay. It seems that the full screen view is
Yeah, exactly. Yeah.
Okay. Sorry for that. So I'll be talking about, as I said, that these are my graphs, a family of graphs, G and vertex set Vn and En. And as I said, the important feature of these graphs is that they are sparse, with the number of edges being of the same order as a number of vertices. As I said, the reason for that is because in applications, we're looking at social networks, for example, the internet graph or the web graph, things like that, where as years pass by, decades go by, the average number of neighbors, the degree of a vertex stays pretty much stable, even though that the size itself grows disproportionately large. So for these kind of problems, also, it's important to have some attributes assigned to the vertices. So here, I'm not just going to be interested in Nerdos Rennie, where the only thing that I care about is the number of edges, but also sometimes the problems that we would analyze have information on the vertices themselves that we're going to call attributes. And these can take different kinds of values depending on the problem, but are in general assumed to take values in a metric and separable space S. And moreover, for the types of graphs that we look at, we allow these vertex attributes to influence the construction of the graph itself. So again, this goes not in the direction of trying to get something very general, but something that is quite specific for many applications, and that is trying to say something meaningful about a general class of processes. So the types of graphs of recursions that I'm looking at, or processes that we analyze, usually fall in the category of a Markov chains on these finite graphs. And in general, I'm going to use this vector xi to denote the vertex attribute, whatever that may be to the application, and information about the in degree and out degree. Just remember, these are directed graphs, so we have two of them. The in degree and out degree are sometimes independent of each other, sometimes they are quite dependent. So some recursions, usually some problems, require using information about the in degree. Some of them require using about the out degree, and we have all sorts of combinations there. The general kind of processes that we're going to look at are essentially Markov chains on these finite graphs, indexed by time k. So here my time index is k. And they are quite general. They are sometimes nonlinear, sometimes linear. And they admit noises both in either the vertices, so this theta ik at time k, or over the edges. So here are these psi ji at time k. And these are functioning as my random fluctuations called, at the end, what we're going to do is we're going to assume that the graph itself is random. So we may have randomness even if there are no stochastic noises. Now, these noises are usually assumed to be IID and independent of everything else, independent in particular of the graph construction. So the graph gets constructed via one of these typical models that we have for the purpose of doing this. And once it's constructed, we run these Markov chain on it. And of course, you're going to end up with, if you're lucky, with some stationary behavior that is describing the behavior of the process R over the entire graph. So this is a vector valued Markov chain with on the space Rn, right, where n is the number of vertices. To give you some examples, I'm going to give you some examples where the recursions have noises and some where it doesn't. Among the ones that do not have any fluctuations other than the construction of the graph itself, we have the PageRank algorithm, the recursion of PageRank, which is nothing but a random walk on a directed graph. A random walk that is tweaked a bit to have this teleportation parameter 1 minus c times qi that allows us to jump when we run out of where to jump to some randomly chosen vertex on the graph according to the distribution q. And this is called a teleportation or personalization value. Other than that, if we look at these recursion, this is saying it's describing the stationary distribution of a random walk where at each step we pick with equal probability any of the outbound links that we have at our disposal. And in case that we're also flipping a coin to decide whether we do the uniform choice among the neighbors or if we choose according to the teleportation parameter. And this constant c determines the proportion of that, that behavior. So this is a random walk. There are no noises, meaning that as a stochastic process, this vector R with component Ri has randomness that is coming only from the realization of the graph itself, not from anywhere else. Here's another example of a recursion that has no additional noises, that again has all its randomness coming from the graph itself. And it's a model for financial cascades that Dio and Junija came up with in 2019. And it's describing liabilities among banks. So here, Ri is the wealth of a bank. The banks are interconnected according to a directed graph G. And there are parameters on the vertices that in this particular model are modeling the assets, the loans, the liabilities, etc., among different banks. Here, it's a little typo. This should be J. The sum is taking over all neighbors J, connecting into I. Here's another example where we do have stochastic noises on the vertices. This is called the generalized de Groot model, and this is a true interacting particle system in the sense that at vertex I and time k plus 1, the value of the process is some random fluctuation depending on what the model is being used for. It's either a function of just the vertex attribute or the noise or both. And then it's going to take an average over all the neighbors, again, with a damping factor here, C, that determines the proportion of that influence that is coming from the neighbors and the proportion that is coming from the random fluctuation. For this model in particular gets used for various things. Among other things, it's been used to study opinion dynamics in the social sciences, and in economics, it has been used to model production networks. Again, depending on what the model is being used for, what the value specifically of these function f takes. So it can be just a noise, some kind of random fluctuation that occurs in the way that we adjust to the opinions of our neighbors, or it could mean something that depends on the vertex attribute itself. So this is the Q, some property of the vertex. Another example in this category where we do have noises, again, noises on the vertices, not on the edges, is the noisy majority voter model, where we can think of all n members of my graph updating their opinion according to the majority opinion of their inbound neighbors. So we take the opinion of our neighbors, all the opinions are either zeros or ones, and if that opinion is greater than, if the majority says that we should vote 1, then we're going to say 1, except we might say the opposite. So this is a little random fluctuation that makes it noisy, and that allows us to get interesting different types of limits than what we would get without the noise. So most of the time we do what the majority says, but on occasion with a Bernoulli or probability epsilon, we do the opposite thing of what the majority of our neighbors say. And again, these are all meant to be in this talk, recursions that are operating on a directed graph. So the only influence that a vertex is receiving is that is coming from its inbound neighbors, not its outbound neighbors. And in general, that is going to allow some interesting simplifications. Okay. So what is the goal here? As usual, what we're trying to say is something meaningful about the stationary distribution of these Markov chain on the graph. And in particular, if you can think of a graph that has exchangeable vertices, where all the vertices are stochastically the same, then it makes intuitive sense that all we really care about is the marginal distribution of one of its vertices. The joint distribution of vertices on this vector R is, of course, going to be determined by the neighborhood correspondence. So if two vertices that are very close, of course, are going to tend to be highly correlated. And that structure is interesting as well. But if you just look at the marginals of each vertex, because all the vertices in the graph have the same behavior, then it is enough to look at one component. And that component is what we call the typical vertex, or the distribution of a typical vertex. And it's nothing else, but we pick one vertex uniformly chosen at random from the entire graph, and we look at the evolution of our process on that vertex. So assuming that the Markov chain on the graph on Rn has a stationary distribution as k goes to infinity, then we want to look at a randomly chosen component of that limit and say something interesting that allows us to do some analysis that provides some insight about what the stochastic process is doing. And how do we do this? We normally do this by looking at a family of random graphs as the number of vertices in the graphs goes to infinity. So this is a standard trick to be able to get some of those very strong correlations among vertices that are close to sort of wash away in the limit and give us a characterization that is useful in practice for computing moments, variances, and sometimes even tail behavior of the distribution of the solutions that we're looking at. What kind of graphs are the candidates for? Well, we're gonna state our main theorems for a class of graphs for which a strong coupling exists. And what is a strong coupling? Well, we normally think about random graphs in the local weak convergence sense, where if I look at a small neighborhood of a vertex and I fix the length of the neighborhood, and I take the limit as this number of vertices goes to infinity, that this neighborhood converges in the local weak sense to some other neighborhood of a bigger object, right? So that's what we call local weak convergence, which gives us some isomorphism between the local neighborhood of a vertex and that of its local weak limit. And we say that we have a strong coupling if, besides having the local weak convergence, we also have that the marks or the vertex attributes also converge sort of uniformly on that neighborhood. So we say that we have a strong coupling if there exists a simultaneous construction of the graph, the original graph, and its local weak limit such that the two neighborhoods for any fixed k are isomorphic, and the distance between the corresponding vertex marks is uniformly smaller than epsilon across that neighborhood. And if you would wonder what kinds of graphs have this property, well, most of the graphs that we tend to work with do. In particular, the Erdos-Renyi graph, the Chung-Lu model, Norris-Reitu model, which are all versions of the Erdos-Renyi graph that allow for inhomogeneous vertices and general vertex attributes. Generalized random graph is another one of those. And the directed configuration model, all of them have this property that they admit strong couplings with their local weak limits, which happen to be delayed marked Galton-Watson processes. And why delayed? Because in most of these examples and most of these graphs, when we sample uniformly at random one vertex, we will have a different distribution for that particular vertex and to any other vertex that is a neighbor. So being a neighbor is actually giving us information about that vertex already, and that changes the distribution of those other points. And sometimes it changes this quite dramatically. So the delay refers to the first one, so the root of usually our Galton-Watson process having a different distribution. So in terms of how general this kind of theory works, well, basically all we really need to make a local weak convergence, including of the processes in the setting, is to make sure that the map that we're analyzing, the recursion, is continuous enough, in particular Lipschitz continuous. So we have a recursion that is determined by a map phi that is Lipschitz on its recursive argument. So on this species, on the G's of R's and the X's, remember the X's are vertex attributes, and that it's also Lipschitz on the R's. So the G also has to be Lipschitz there. Then that's usually enough to give us control over what the recursion is doing to be able to obtain strong local convergence theorems for these processes. We also need some growth condition sort of related to the Lipschitz condition that tells us that we have an upper bound or a way of upper bounding the fluctuations that are coming from the noises. And the graph itself needs to have enough properties, so that the recursion itself has to have enough properties to ensure that the Markov chain is going to converge. One such condition would be to ask that the matrix that is relating these upper bounding functionals, sigma minus and sigma plus, has either bounded p norm on any graph or on the graph that we're interested in particular. This tends to be true of all the examples that I gave you. These are all Lipschitz recursions, and this condition is sort of trivial for all of those. We also need some basic initial condition for the starting values that we give a time zero to our recursion. And again, in terms of the matrix notation, it comes down to asking that these other matrix also has bounded p norm. Again, these are bounded, not necessarily contracting. So of the examples that I gave you, 3 of the 4 will have these constant k and k0 to be strictly smaller than 1, which would naturally tell you that the recursion is contracting. And one of them has k equals to 1, so it's not contracting, but it's still Lipschitz. The local results only require that it be Lipschitz. So what does the main theorem tell us? Well, it says that if we are interested in analyzing the stationary behavior, or even before that, a finite number of iterations of our system, of our Markov chain, over a randomly chosen vertex I, uppercase I here, and our graph is such that it admits a strong coupling with its limit, which is going to be assumed to be a Galton-Watson process or a marked delayed Galton-Watson process, assuming that the recursion phi satisfies the conditions that I mentioned, and that the attributes are well behaved. Again, these are sort of standard regularity conditions for ensuring the pth moments of these functionals, sigma minus, sigma plus, and the beta. So nothing that is very hard to check in practice. What we're going to have is that the behavior of a typical particle I of this stochastic process for a time k converges in a very strong sense in the Wasserstein metric of order p, whatever p you were able to find in the assumptions, to some other random variable that I'm going to call R empty set k, which is defined on the limiting object. So the limiting object in this kind of graph is always a Galton-Watson process. Hence, this R0 is defined on a much more tractable graph than the original one. So if you think about it, what is the strength of having a theorem that, like the one I just described? We're interested in the typical behavior of each of the vertices, or all of the vertices in this case, because all of the graphs that admit a strong coupling are going to have exchangeable vertices. So if we're interested in the marginal of 1, what this says is that the graph can be complicated. It can have cycles. It can have multiple edges. It can have all sorts of complicated things. However, for any fixed k, it is enough to look at the limiting object, which happens to be a Mark-Galton-Watson process. And once you're in the Mark-Galton-Watson process, then analyzing the problem allows you, comes in with a whole other set of tools that we have at our disposal. So this is some way of translating the finite graph problem to the infinite limit problem. And although it's infinite, it's a tree, and it has a lot more structure to work with than the original graphs that we were looking at. So once we are on the tree, you would say, well, what do you get out of that? Well, what we want to get out of this is a characterization that is useful for something that you can go and say, well, here's my limit, and from this limit, I can compute means, variances, third moments, fourth moments. I can tell you whether it has exponential tails. I can tell you if it has heavy tails. If it has heavy tails, I can tell you exactly, sometimes with some luck, the exact tail distribution of that solution. So having that limit, this characterization allows quite a bit of information about the original problem that we were looking at, even though the original problem lives on a graph, on a finite graph. It is closely related to the existence of multiple solutions, to the existence of something we call endogenous solutions. So really being able to translate this and having a characterization like the one we're gonna have here is quite useful in practice. So what is it that we're asking for? We're asking that the recursive map that we're working with, when we take the composition of this function g with the map phi, which I'm going to call it map psi, that this map defines a contraction under some metric. It doesn't have to even be the same metric as that we use to establish the local limit, but it needs to define a contraction in order for us to do the simplest kind of argument to prove the existence now on the tree as k goes to infinity to some limiting object r star. So this, if you think about it, it's a commuting diagram where we're taking two limits of interest, one in k, which is time, and one in n, which is the number of vertices on the graph. So with this, what this is going to allow us, is going to tell us that if you want to go into the infinite limit as k goes to infinity, fixing n, it suffices to first take the limit in n, then take the limit in k in the limit, and then you'll be able to go back to having some very good information about the limit on your graph, assuming that the number of vertices is large. So when we have this map and we have a contraction, then we can establish the existence of this object r star. If it's not contracting, then there are other tools at our disposal. Usually many of these recursions are monotone maps. So we add usually a combination of monotonicity with well-behaved initial conditions can also lead to the existence of r star. Moreover, once you have this characterization, it turns out that the representation of this limit r star is explicit in terms of the original map phi. And then this map phi is now a function of these other IID random variables VJs, which have a characterization of their own. And that characterization is the following. These VJs are IID independent of the vertex attributes of the root. So the x0 are the vertex attributes of the root. And they happen to have the same distribution as the attracting endogenous solution of the stochastic fixed point equation described by these. So V has the same distribution as phi of some vector y that is going to be a function of these x's and the in degree and the out degree and the noises of copies of itself, right? Over the set of vertices that are inbound neighbors, which in a tree are just the offspring. So how many offspring? N. Why are these two separate? As I said, this has to do with the fact that the root always has a different distribution and tends to behave a little bit differently. So the fixed point equation is not satisfied at the root level, but it is satisfied at any vertex other than the root on our infinite tree. So now we have this fixed point equation. As I said, this is useful if you want means, take mean, the expected value on the left, expected value on the right. And if this is linear, you can compute it exactly. If it's non-linear, you can at least get upper bounds and lower bounds. Do the same thing for the variance, because now you have systems of equations for all of these quantities. And it also works for the tail distribution. If the solution V happens to be, let's say, a heavy tail distribution, then this also becomes quite tractable to work with the recursion itself, with this fixed point map. So that's the essence of the theorem, as I said. It's a translation theorem that allows us to go from a problem that lies on a graph that has self loops, that has multiple edges, that has short cycles and principle, to something that can be characterized in an infinite Galton-Watson tree that allows us to use the techniques that are native to the Galton-Watson process. And the one thing that you think like, well, why is that characterization so simple? And where does this go from here? Let's consider the simplest generalization of that problem that I just stated, which is to allow the recursion itself to depend on its own history. So in all of the examples that I showed you, the value at vertex I at time k plus 1 depended only on the values at the previous time k of the neighbors of I. So this set j connecting to I, right? But it did not depend on the history of I itself. So in some cases, some recursions are important to consider that they're sort of learning from their own history, or maybe taking an important contribution of their update is whatever their previous value in the time step before was. So when we add that possibility, the problem actually becomes a lot harder. And then the interactions become a little bit more difficult to analyze. The general case where we have an undirected graph is even worse in the sense that when I add this element, not only am I getting interactions from my inbound neighbors, but in the next step, I will get interactions from those back, right? So I go first, if I'm a vertex and I give my interaction to my neighbor, then in the next step, I get that interaction back. And this becomes a very, very difficult problem. So the first thing to study is this case where you have just the directed graph still, but this self-interaction or sort of drift term that depends on the vertex itself. It turns out that when this happens, the problem becomes more difficult. The characterization that I talked about disappears, so it's no longer true, but the directed nature of the graph still allows us to say quite interesting things and establish the existence of a stationary distribution. So that's one of the current problems that I've been working with, in particular with opinion models like the DeGroot model and some of its generalizations, where you do allow the self-learning, and that still allows you to establish something about the limiting behavior as k goes to infinity. The general set of theorems beyond the directed case are actually set up for undirected graphs, where these local interactions become more complicated because of the fact that whatever I see right now on time k, I will see it back from the same people, the same neighbors, but on the opposite direction in its time k plus 1. In that case, these kind of translation theorems are still useful, because what one can prove is that as long as the graph belongs to an Erdos-Renyi or a configuration graph or any of these other versions that have as their local weak limit a Galton-Watson process, then what happens there is that we can always ensure that the analysis of the object that we're interested in can be translated without any risk to the analysis of the process on the infinite limit. So again, this is a question about trading a graph that has cycles to the tree that does not. So in all of these examples that I gave you, our graphs tend to be simple with high probability or by design. And it's important to think that, again, what we're interested in this local limit is that we're going to be looking only at finite neighborhoods of a Galton-Watson process. And there's more hope there to establish existence of stationary behavior than there is on the graph itself. So in terms of future work, the first one, current work, is to incorporate in the directed case the drift term or self loop, and in the general case to try to find useful characterizations when the graphs become undirected. So those are all interesting avenues, and it's quite sort of new work. There's several people who are working on this kind of problems. Again, the key being that unlike most of the mean field theory kind of results, these are sparse graphs where the local properties of the vertices matter a lot. And the dependence among close neighbors does not actually disappear the same way. You don't have asymptotic independence, so the goal is different that in that context. And I think that's why it's sort of the newest, and it's a challenging set of problems to look at. That's all that I had for today. So if you have any questions, I'll be happy to answer.
So let's thank Mariana for this nice talk. So you have any questions? So about this, I want to ask you about this this open problem that you mentioned, that was the interaction with himself, the graph itself. No? So I was thinking about that. For example, you mentioned the voter model, and the voter model falls into your category. And a popular model which does not fall into the category would be the contact process, right? Because then and this is somehow the simplest model I can imagine, on which you have this self-interaction mechanism. So could you say something about that, or is it still far from?
Well, that's not my work. I can tell you a bit about what is known. The most recent set of results for that kind of more general setting, again, on an undirected graph, are by Kavita Ramanan, Daniel Lacker, and Ryu Wu. They have quite they have like at least 3 or 4 different papers where they've been looking precisely at that problem, where you have the ability to incorporate some of these other interacting particle systems on undirected graphs. The main challenge, as I said, comes from the fact that on an undirected graph, your interactions, you get your neighbor's feedback on one time k, and then you will give it back at time k plus 1. And that sort of course, creates a lot of problems. Time can be continuous or discrete, depending on what you're looking at. But in that case, these useful characterizations that I gave here disappear entirely. So the question becomes more, I would say it's farther behind, in the sense that what those theorems establish is the local weak convergence of the whole process to the corresponding limiting tree. So you can look at the contact process, let's say, on a finite graph, and argue that it suffices to look at it on the infinite tree. But once you're on the tree, the problem's still hard, right? And it's still not trivial to establish what kind of stationary behavior, if you have any, and that kind of thing is. But it becomes sort of it becomes a problem about studying the tree itself. So it's in the translation step. So it's the main theorem that I gave that does exist for undirected graphs and for diffusions as well. So it doesn't have to be discrete time. But what you will lose is the characterization that becomes immediately useful on its own, which is this stochastic fixed point equation that there's no hope of it holding. So the limit is a lot more complicated. And I believe even establishing the limit as k goes to infinity in the infinite object might not be true in many cases.
And also, I have another question, which is that so this analysis sometimes people are interested in things like the mixing time of the chain or things like that. Here you can answer a weaker question, but could be still interesting, no? Which is the time that you need to equilibrate this particular variable that you are looking at, no?
Yeah, so there are questions about the mixing time. In this case, some of these examples are all contracting. So once you have the contraction, for example, that is less of an issue to know how far you have to go, right? Like if I only want to look at, if I'm interested in the limit as k goes to infinity on the finite graph, it is actually fairly straightforward to argue that all you need is k to be, 10, 20, sometimes 100 steps to be able to get very close to that limiting behavior. So it's sort of a cheating example where you don't necessarily have to wait that long. The moment that you lose a contraction, then of course the mixing time becomes another issue, because then you don't know how far you have to go before you can close the commuting diagram for the different limits that are being taken, right? And yes, I can tell you that there are people who work on that. Some of the techniques that are used for these local limits for fixed k are also useful for establishing that. Like that is true for like the random walk, the PageRank random walk on a graph where the damping factor is equal to 1. So it becomes, you lose a contraction, and definitely having those local weak convergence theorems are still very useful, but they don't give you the entire story.
Well, so if there are no more questions, let's thank Mariana again, and also thanks all the speakers of today's session. So